Welcome to lecture 4. So today we are going to see inference with these penalized regression models. We are going to focus on lasso and adaptive lasso. And during our live session on Friday, we can talk more about other estimators, right? So basically, what I'm going to present to you today is the distribution of the lasso estimator in low dimensions and the distribution of the other lasso estimator in high dimensions and a very general setup. Two main references. One is a paper by Knight and Fu in the Annals of Statistics, and one is a paper that I wrote with Eduardo Mendes, and it was published in 2016 in the Journal of Econometrics. Okay. So let's start with the theory for the lasso, the asymptotic distribution for fixed P. Okay, what's P? P is the number of variables. Okay. And what's S? S is the number of relevant variables. Okay. The non-zero, the variables with non-zero coefficients. So we are in a setup where these numbers are fixed. So we are in a low dimension setup. Okay? So what we have here, what are the assumptions? We have fixed design. So we are assuming that X, the vector X is repeated, is fixed in repeated samples. Okay? And we are assuming the same regularity conditions as before. The sample covariance matrix converge to sigma, and where sigma hat is 1 over t x prime x, and 1 over t the maximum in t of xt prime x goes to 0 as t goes to infinity. So there's some kind of bounds on the quadratic variation of the axis, right? If x is stochastic, it's kind of something related to the variance of the covariance matrix of the axis. Okay? So both sigma hat and sigma are non-singular. Okay? And what we know that in this setup, OLS works because we are in a low dimension, and we know the square root t beta hat OLS minus beta naught. Beta naught is the true coefficient. This converges in distribution to a Gaussian random variable with mean 0 and covariance matrix given by sigma square big sigma minus 1. And what's a sigma square? Let's remember that we are in a linear regression framework, okay? And we say that the u prime is sigma square I. Okay? So it's the variance of the errors in the linear regression. Okay? What these authors they found, okay, is that under the previous regularity conditions, if there is a sequence of lambdas, the penalty parameter in the lasso, again, what's our optimization problem? We are minimizing x beta square plus lambda L1 norm, right? So what we know that when we have a sequence of lambdas and this sequence converges to a constant lambda that's equal or greater than 0, beta hat will converge in probability to the minimum of a population cost function that's given by this expression here, which is basically a quadratic form of beta minus beta naught, okay, plus the penalty, okay. If the sequence lambda goes to 0, then we can show that the argument that minimizes this quadratic form is just beta naught. So beta hat will be consistent. Okay, if you are interested in the proofs for these results, there's a set of slides in our Google folder where I highlight the main steps of the proof for this result. Okay, so basically, and it's kind of intuitive, the result, right? If you in the limit, if you take your penalty to 0, it means that in the limit you are running OLS, right? And under our assumptions, OLS of course will be consistent. Okay. But the key thing is when you have a lambda that's not 0, right? When it converges to a lambda naught. And in this case, what's going to happen, okay, is that in terms of distribution, square root t beta hat minus beta naught will be converging distribution to the argument that minimizes this function v of beta. And what is v? V is a term here, is a quadratic form, okay, that's the constant. He is not depend on beta, but does not depend on anything that's random, because sigma is not random. And there's a component here that depends on a random variable v, that's a Gaussian random variable, multivariate Gaussian variable. So what we see is that the distribution, okay, of beta hat will be something that's a Gaussian plus this additional term here, which will serve a kind of a spike. So what happens is that the distribution of the lasso estimate will be a combination of a Gaussian random variable for the non-zero parameters, for the parameters associated with the relevant variable, plus a spike on 0, a mass point over 0 for the variables that are irrelevant. So it's a mix of these two distributions. So of course, the overall distribution of the lasso is not Gaussian. Okay, but what we can see from these results that if we conditional on the correct selection, if you say, okay, but I just want to look at the distribution of the relevant variables, then the distribution of the relevant variables will be Gaussian. Okay? So this is an important point here. So the last theorem shows that non-zero parameters are estimated with some asymptotic bias. Okay, and what we can, if we suppose that the true beta naught on the irrelevant set is 0 and on the relevant set is different than 0, then the function v is given by this expression here, and by uniqueness of the solution to minimum of a function v of alpha, if we have one of the coefficients of the irrelevant variables will be 0, if and only if this condition holds element-wise. Okay, and similar results will hold for large P and S, but as we are going to see, these results are non-uniform. They are not. They are. We cannot guarantee that if we do not condition on the correct selection of the model, then the distributions can be much more complicated than normal, and inference will be tricky, right? So the message from this paper here is the following: relevant variables, coefficients goes to a normal. Irrelevant variables, you have a point mass at 0. The overall distribution is the combination of the two. Okay, and this was proven. This was proved. Sorry, for low dimension setups. There are some theory extending this for large dimensions. So now we're going to make kind of a big step here. I'm going to show you my paper where we proved some interesting results for the adaptive lasso in a very general setup that's more interesting to financial applications. Okay, so it's basically this paper with Eduardo Mendes. So we are in this high-dimensional time series model. So we are considering that the data are formed by time series. Okay, we have, it's a linear model, but with lots of variables, many more variables than number of observations. Okay, and we are going to consider the adaptive lasso. Why the adaptive lasso and not the lasso? Because the lasso requires the irrepresentable condition, and we want to avoid the irrepresentable condition. So we want to consider cases where our variables are really highly correlated. So to avoid the irrepresentable condition, we are going to look into the adaptive lasso. Okay, and furthermore, we think about applications in finance. So the error term in the regression can be non-Gaussian, heteroscedastic, and the number of included variables can grow polynomial with the sample size. We have also results for exponential growth, okay? But then we have to impose more a set of more restrictive assumptions. Basically, to achieve this bound here, exponential growth, we will need some sub-Gaussianity assumption. If you want to let your variables, the distribution of the variables and the error term to go free, and then you have to restrict the number of variables that you have in your model. Still, you can have many more variables than observations, but they cannot grow at exponential rate. They can only grow at a polynomial rate. Okay? And what we are going to show is basically that the adaptive lasso is sign consistent, and it has the oracle property. What's the oracle property? Is that the distribution of the lasso estimates for the relevant variables is asymptotically equal to the OLS distribution in a regression where we include only the relevant variables. Okay? So it's basically saying the following. Take your quadrillion variables, run an adaptive lasso, the distribution, the asymptotic distribution for the non-zero parameters will be the same as if we knew the right set of variables. And if we were just running an OLS regression with the right set of variables. Okay? So this is a pretty good property. What I'm going to show is that it's good in some sense, but there's a strong assumption like that it to be necessary for the result to hold, and also this is conditioned on the right set of variables. And I'm not talking about the overall distribution like relevant and irrelevant variables. These are just for the relevant variable, just for the selected variables. Okay? And in the paper we conduct an inflation forecasting exercise. Okay? That if time permits, I can go through the example here. Okay? So basically we have like 4 sets of assumptions in the paper. 2 sets of assumptions are related to the data generating process, how the data have been generated. Okay, so basically we require assumptions on stationarity. Our paper is about stationary data, and also we have like to bound somehow the persistence that we have in the data. How far back in the past we can remember. Okay, and this will be important. Furthermore, because we are not going to impose normality anywhere, we need to come up with another set of assumptions, and these assumptions will be about the moments of the distributions of the variables, both the dependent and the independent variables, and also the error term. Okay, so we need to impose some moment restrictions. Okay, and this is the tricky hypothesis that I mentioned, lower bounds on the non-zero parameters. Okay, we cannot handle smallish coefficients. So if our true parameters are really, really small, we won't be able to detect them. So this is a problem. So we make this assumption that in the nature, in the true model, the coefficients of the true model are not too small. Okay, if they are different from zero, they're kind of far away from zero. And we derive the bound in the paper. What do we mean by being far away from zero? Okay? And then we have eigenvalue conditions, like restricted eigenvalue. We need curvature, so you are all now familiar with these eigenvalue conditions. Okay? We need assumptions on the adaptive lasso weights. And we, in the paper, not going to talk here, but in the paper we show that if you use lasso to construct the weights for the adaptive lasso, as I mentioned last week, so we prove here that if you use lasso, then this assumption on the weights will be satisfied. Okay, and we have an assumption on the regularization parameter that's highly technical, and just basically it says that okay, there exists an amount of regularization that will make the theory go through and the theory works, right? But in practice, you are going to select the lambda by BIC or cross-validation, your favorite. Okay? So basically the assumptions is that if we, again, what's our regression? Right? We have here our parameter x beta plus ut, so this is the error. Basically, we're assuming that the set of variables are weakly stationary, and the error is a martingale difference, and then we have like kind of two hypotheses here. Okay, let's go for the fourth one. Basically, the fourth one is kind of a moment condition. So these are moment conditions. And this is because we are not assuming any distribution for x of u, for the joint distribution of x and u. So we have to assume that some moments exist. Okay? And the fact is, why this is important? I mean, you may think, oh, good Lord, why? I want to run this in real life, in practice, and this crazy guy is just showing me moment conditions. Why is this relevant in practice? Because this will be related to the number of variables that you may allow in your model. And the larger is the value of m, okay? Basically, the larger will be the number of variables that you include in your model. But of course, you cannot have certainty about the value of how many moments do you have, because you don't know the distribution and u is not observable, right? So you only observe x. But if you take your data, y and x, and you look at the empirical distribution of this data, okay, if they look more or less like a normal random variable, then maybe you are pretty good. Probably m is quite large, right? But if you look at these distributions and they have ugly tails, like very fat tails, outliers, and they are asymmetric, and so they look like very different from a Gaussian. Probably, or the value of m is not that large. So if still the adaptive lasso will work, but there won't be hope to do correct model selection. For instance, if you have like 20 observations and 20 million variables, okay? It will be just impossible. Okay? But you still can have like 100 observations and 300 variables, and it will work quite well. Okay? So this is a condition about moments. The third condition is about tails. Basically, what we say here is a condition on the tails of x squared, okay, and on x. So it's related to how what's the decrease of the tails. What do I mean about that? Let me try to draw a Gaussian here, right? So you have a Gaussian random variable here. This is the tail behavior. The tail behavior is how fast, okay, the tail goes to 0. So it's this limit here. In a Gaussian, it goes exponentially fast to 0. You can have a variable that goes faster than the Gaussian, or it can go slower than the Gaussian. And you have another bound. So how these things decrease? So it can be really slow. So you can have like things like that that's kind of really thick tails, right? So basically here what's saying that it's a tail behavior, it's a tail condition. So we can have something that's not Gaussian, but we cannot have something that's kind of like a Cauchy random variable, right? So basically in practice, of course, nobody that will apply this in practice, or imagine you are a risk manager in a hedge fund, then you have to estimate lasso for your data. We are not going to be checking these things. But what you can say is how much trust you can put in your model. So it's going to be a trade-off on how well behaved is the data, on how many observations do you have, right? And how many variables do you have? So there's also a trade-off. If you have large number of observations, small number of variables, then you really don't have to bother. If you're in the other way around, small number of observations, large number of variables, if it's too large, then you need something like Gaussianity. So you need to hope for Gaussianity. So you need that your variables look more or less like a Gaussian. Okay? But if they don't look like a Gaussian, you can still have more variables than observations, but there's a limit. You can have like 2 times, 3 times, 4 times more variables, but you cannot have like 10,000 times more variables than observations. There won't be any hope to do anything meaningful with that. So basically these assumptions, like what is the kind of the takeaway from here is that the uglier the data look like, less variables you really can include in the model. Okay? If the data look like more as a Gaussian, then you can allow for more variables. And this is something that you're going to learn by doing in practice during the assignments, during the midterm, and in your work life, right? Estimating this kind of models. Okay? So basically, let me go fast here. Okay, there's also assumptions about the beta mean. This is the assumption that I told you, that beta mean is a kind of lower bound for all the parameters that are in the relevant set. Okay, and assumption 3 is something related like to the restricted eigenvalue. I don't need to go through them here, so it's really technical. Okay, so one thing that's important is assumption 2, and this is important in practice. So you have no hope to identify effects that are truly small. And how small? Something that will be of the order of 1 over square root t. Okay. If this is the case, lasso, adaptive lasso, all these techniques will set it to 0. Okay. So anything smaller than that, it will be set to 0, more or less. Okay? So this is basically what's written here. And then we have assumptions on weights. Okay? And basically, lots of things here, lots of numbers. but the message is you need to select weights that penalizes irrelevant variables the most and penalizes the relevant variables the least, which is pretty obvious, but this is all written in terms of the parameters of the model, so you may forget about that and say Lasso produces good weights in the first step. So if you take Wj, beta j, Lasso, and you wish to avoid the mistakes, so you sum here 1 over square root t. If you have these fantastic weights, okay, it will satisfy these two ugly assumptions that we have in the paper, okay, and that's what we explain here. Here's the ugliest assumption in the paper that's related to lambda. So lambda is related to sample sizes, number of moments, and whatever. Again, forget about this. There exists lambda such that the Lasso works, right? So that's basically what we show in the paper. Okay? So you don't have to bother about that. Okay? So in the end of the day, what do you have to bother? Beta mean, distribution of the data, persistence in the data, how dependent on the past, okay? But basically, if all the assumptions were true and beta mean is larger than this quantity here that depends on sample size, regularization parameter, sparsity, okay, we show that beta hat, the Lasso estimate, is sign consistent. Basically, we are doing model selection right. Okay? So we are right on spot to get the true model. Okay? And furthermore, the asymptotic distribution of the Lasso for the relevant variables, important, just the relevant variables, is the same as the asymptotic distribution of the OLS using the relevant variables. Okay? And we prove that in a very general setup with polynomial case. What's the polynomial case? Is that P, number of variables, is a polynomial function of t. So for that, what we need moment conditions only. We don't need the distribution of the variable, the joint distribution. We just need moment conditions. Okay? Let me show you a simulation. And a simulation that it's interesting because we are going to simulate cases where our assumptions are not valid. Just because our assumptions are just sufficient, they are not necessary, right? So even when our assumptions fail, I'm going to show you some interesting results. So how it works. We have our dependent data is y. It has an autoregressive term here, okay? Plus, it loads on a number of variables x that I'm calling x1. One here means the relevant ones, okay? Plus an error term. The error term follows a Garch-1-1 process where you have a volatility function that's given by these parameters and times a random term that's a distributed error with 5 degrees of freedom. So it's set tail. And with this volatility function means that this U here does not have the fourth moment. So it's an error with the distribution of this error is really thick tailed. So it has like really thick tails. So it doesn't, this error doesn't have like the fourth moment. So not even assumptions for OLS to hold fails here. Okay? And the x's are dividing the x's relevant and the irrelevant, and they all follow a VAR of order 4, also with t-distributed errors, right? We are setting phi equals to 0.6, and this vector beta is given by this expression here, where s is the number of relevant variables. So what we are going to do, we are going to simulate this model for different scenarios of total number of observations, number of variables included in the model, and number of truly non-zero variables, so the number of relevant variables, right? And we are going to look at two things. One is the estimator of this parameter phi here. How close we get to 0.6, how close we get to the oracle. The oracle means that we are running OLS under the assumption that we know the set of true variables x1 here. Okay? We are also I'm going to show you statistics about model selection. How good is model selection in this setup? Okay? So let's go look at pictures here. So basically this picture, each column represents a number of relevant variables. Okay? We are considering t equals to 50, so 50 observations. So here is s equals to 5, s equals to 10, s equals to 15, s equals to 20. That's the number of true variables, non-zero variables. And here the total number of variables, 100, 300, 1000. Okay? Remember, only 50 observations. Okay? Red line is the oracle. Blue are the lasso. For what? To estimate phi. Okay? And phi, the true phi, is equal to 0.6. What we can see here, that the results are only really good when you have only 100 variables and just 5 relevant. But in a way, but it's still 2 times more than the sample size, so it's really a high dimension. But the number of variables that are relevant is just 5. So you see the blue curve is a little bit left shifted to the as compared to the red curve, so there's this bias. But you see that the bias is small if you look at the x-axis here, so it's not big. But when we start to include s, increase s, what you see is that the distribution gets like, the range of the distribution of the blue distribution gets wider, right? Why is that? Because it's adaptive lasso is starting to make mistakes. Instead of estimating phi around 0, is setting phi equals to 0. That's why we are going this direction. And then when you increase the number of total variables, you start to see a mass over 0. And that's because you are in a situation where the hypotheses that we had before are kind of failing, and we have a strongly non-Gaussian process. So you have just t equals to 50 observations. So it's really, really small. So you can see that the asymptotic theory is a bad approximation. But still, in one case, we can have a good result. Okay? And you can say, okay, with 50 observations, you are not going to include more than 100 variables. It's kind of be not fair to the model. and you're not expecting to have much more than 5 relevant variables. Okay? With 10, it's okay, there's some outliers here, but still you see something that's close to the true value here. More than 10, then it's a total mess. Okay? But it's for 50 observations. Now I'm going to show you other pictures increasing the same structure, but I'm going to increase the value of t. Okay, so we are going to increase the number of observations. Then it's for 100. Oh, it's much better here and here, right? So basically here we have the same number of observations and variables. So it's 100 to 100. So right on spot. For 300 over 100, the point mass in 0 vanishes at least in the 2 cases, but there's a small bias. But you see, the bias are really small, because here's the average, of course, is in 0.6, but here, if we look here, is 0.59, because this number is 0.58 and this one is 0.6. So it's a negligible bias, right? It increases, of course, as the model complexity increases. Okay. And now with 300, it gets pretty good. And again, here, it seems that the bias is huge, but look what we have here. This point here is 0.56. So we are talking to a bias that's less than 0.01. Okay? So it's pretty good. And here's for 1000. So we can say that the theory is working, even in this very bad environment where we are kind of having the error term has no fourth order moment. So one of our first assumptions only holds for m equal to 3 at most. Okay? So it's a very, very difficult problem, and the results are quite reasonable. Okay? And if we look at bias and MSEs of all the coefficients, all the betas, you see the bias is all of the order of 10 to the power of minus 3, and the mean squared error is also to the power of 10 to the power of minus 3. So pretty small numbers, right? And they go almost to 0 when we have 1000 observations, showing that our asymptotic results are kind of kicking in. Now it's interesting, okay, but let's talk about correct sparsity pattern. What's correct sparsity pattern? That we are doing the model selection right. We are selecting the right variables, and we are excluding also the right variables to exclude. And what we can see is that for t equals to 50, we can do reasonably well here and here. So with s equals to 5 or 10, and p equals to 100. So we are kind of good. And if we are kind of less rigorous, we can say that in this situation we are also good. Of course, when you go to 1000 variables with 50 observations, there's no hope, right, to do anything right. But as we move to the right, as we increase the number of observations, then you see that here we are doing bad only if we have 20 variables relevant, right? But otherwise we are doing pretty okay. And in the limit with 1000, then we are just perfect. But this is the correct sparsity pattern. So we do not miss any relevant variables, and we exclude all the irrelevant variables. Now let's look at a less ambitious goal, is that look just for the true model being included, if we are selecting all the right variables. So in this case, we see that we are doing pretty good here, right? And also in most of the cases here, apart from these two cases, we are doing pretty good here, and of course here all the time. Okay? And if we compare with panel C and D means that what are the fraction of relevant variables included and what are the fraction of irrelevant variables excluded. Okay, and you see that in some cases you're just missing some of the variables, and if you miss one variable, like in this case here, you're not going to have correct sparsity pattern because you need the exact true model. So panel A is really ambitious, okay? And you are basically what's saying that we are doing not the exact correct pattern because we miss one or two variables. We don't miss much, right? Even in these pretty negative cases, like with a very small number of observations, we are not that bad. Okay? We are missing some of the variable, but because we here in this case here, let's say you have like only 50 observations and we say that 20 variables are relevant, that would be a problem that's impossible to correctly estimate, right? It's too ambitious. But apart from these cases, we are doing pretty well. And here's just a table showing average number of variables included and average number of irrelevant variables included, just to show that things are going to the right place, right? In the limit, we are selecting exactly the right set of variables and excluding the right set of variables. And also, in terms of forecasting, we show that our forecasting error, see here, is approaching to get to the oracle one, the theoretical one. So it's doing right, okay? This table is interesting. I'm going to zoom in there. It's an additional result from a book chapter that I have with Anna Spock and Gabriel Vasconcelos, where we extended these simulations also to include like elastic net and adaptive elastic net and ridge and lasso, okay? And let me show you something. Let's focus on this panel here. This is the correct sparsity pattern, the same DGP, right? Of course, ridge will never do model selection right, okay? So you see all zeros as expected because it's not removing any variable. Lasso is also doing pretty bad. See? Zeros everywhere. But then, and one of the reasons you say, because the variables are too correlated. Okay, so let's do elastic net, like people claim elastic net solves the problem of correlation. You see here a bunch of zeros. Okay? But then you go to adaptive lasso. Oh, we start to get large numbers, close to 1. And then we go to adaptive elastic net. Oh, same thing. So what's doing the trick is not elastic net or lasso, but it's the adaptive thing. Making the methods adaptive, creating these weight functions is what is allowing these methods to perform much better. Okay? I'm also going to upload this book chapter on our Google Drive folder. Okay? So I also have an inflation forecasting exercise where we are forecasting monthly inflation starting 1960 until 2011. Our dependent variable is the US CPI for all items, and we are considering 4 legs of inflation plus 4 legs of 130 explanatory variables, and we are doing one step ahead, forecast starts in 2000, okay? And we are doing kind of rolling window. We are keeping the number of observations fixed, and we are kind of rolling window, like the same approach you did in the assignment, right? And basically what we can show here is that adaptive lasso and lasso do much better in terms of all these measures as compared to benchmarkers that are including all regressors, an AR4 or factor models, okay? And both are the values that are the models that the best performing. What's the difference between ADA lasso and flexible ADA lasso? ADA lasso, we are using the lasso to select the weights. Flexible ADA lasso, we are using elastic net to set the weights. And they perform more or less the same, okay? And let me skip this, but this is just the absolute errors of the model over the forecasting period. You see that they start close to each other, but then there are some points where the adaptive lasso detaches from the other models. This is for absolute errors, this is for the squared errors. Okay? And these are the number of parameters selected. You see that the adaptive lasso selects less parameter than the other two models. Okay? And just to see that we have like around 500 variables in total. And the final model, we are kind of change something that will, the number of variables will be something between 7 to 20. So highly sparse, the final estimated model. Okay? So that's all for now. We are going to move forward to the second block. In the second block, we are going to look on how to conduct inference, considering that we have conducted model selection before. So we are selecting variables before. Okay? So thank you. See you later.